Welcome to Tollefson Physics. So what we're going to do today is we're going to apply Newton's second law to situations where the forces are unbalanced. And so if we know the mass and we can figure out what's going on with the forces, we'll be able to predict the acceleration. So those are the type of examples that we're going to look at today. Now let's look at an example where I have a block, and this time I'm going to say that this block is on a frictionless hill. And so this block is going to accelerate in the direction that I drew there. So once again, we're going to go ahead and draw a force diagram. And so force diagram that I'm going to draw, here's my center of mass, and yes, we're always going to have a force due to gravity. And I can calculate the force due to gravity in this particular case. It's going to be 100 newtons. All right. I like to put a little dotted line so I can keep track of where the slope is, because the normal force that holds the block from going into the surface is going to be perpendicular. It's kind of wiggly, but it's perpendicular. And that's it. Those are my only two forces, because I said this is on a frictionless hill. And so because it's on a frictionless hill, it's going to accelerate downhill. Well, how do I know that? Well, I'm gonna come up with, so it's not going to accelerate away from the hill or into the hill. So I'm going to create a coordinate system that follows the hill. So I'll call along the hill X, and I'll call perpendicular to the hill Y. So the normal force is in the Y direction, but the gravitational force is not. And so what I'm going to do is I'm going to resolve that into forces. So I'm going to draw a force arrow. So this is a force of gravity in the Y direction. And then, and it follows, right? It follows the Y coordinate. And then I end it in just the right place so that I can draw in the X direction to get back to where the end of the arrow is. And so this is the force of gravity in the X direction. All right, and then what I can do is I can write some equations about this situation. So it's not accelerating into or out of the hill, so I know that the normal force is going to equal the force due to gravity in the Y direction. And then the other one, that's unbalanced. I don't have an uphill force. So it actually turns out that that is my net force. So if I want to figure out something about acceleration, which is F net divided by mass, and this once again will be in the X direction, then I need to know what is that component of the force due to gravity in the X direction divided by the mass. Okay, so to be able to solve this problem, I didn't give us an angle, so we're going to give an angle to the hill. So angle to the hill, let's just make it a nice 30 degrees. Okay, and so convince yourself that that 30 degrees will be right here, which I'll just write as theta. So right there is going to be 30 degrees based on 30 degrees being right here. Okay, so I want to figure out the acceleration in this particular case. Well, the force in the X direction for the force due to gravity is on the opposite side. So opposite divided by hypotenuse is related to the sine. And so what I'm going to rewrite this is my FG really is the force due to gravity times the sine of 30 degrees, and that'll be divided by the mass. So in this particular case, FG is 100 newtons, sine of 30 degrees is the number 1/2, and the mass is 10 kilograms. All right, so 100 divided by 10 is 10, and then divide that in 2. So my acceleration is going to be 5 newtons per kilogram going downhill, which that is the same thing as 5 meters per second squared in the downhill direction. All right, so 2 examples. I showed you 2 examples of situations where I've got a known mass, so I know something about the amount of the object that's there in kilograms, and then I know enough about the forces to be able to predict something about the acceleration using Newton's second law, where the acceleration equals the net force divided by the mass.